Well, last lecture we started correlated equilibrium, but I was in kind of a rush. So after the lecture, when I talked with several of you, I've had a feeling that things didn't work out well. So we'll start, but this time, last time I said, well, we chose the approach which was mathematically more simple, but intuitively, application-wise, less relevant. Today, we'll do it the other way around. We'll take the approach which is mathematically more sophisticated, but more intuitive, okay? So we'll start over again from correlated equilibrium. Equilibrium or solution concept. Okay. So again, the idea, let's start with the example that we were working with last lecture. We were considering the battle of sexes game, which had this structure. So we already discovered that the mixed extension of this game has 3 Nash equilibria. Both plays S with probability 1, both plays O with probability 1, and then player 1 probably plays S with probability 2/3 and O with probability 1/3, and player 2 plays S with probability 1/3 and O with 2/3. Okay? So again, the idea of mixed strategies is individuals randomize their strategies in an independent way. So they use independent random devices to decide whether they would take the action S or take the action O. Okay? So rather than using independent random devices, why not choose or use a common random device and coordinate their actions based on the outcome of that common random device. Okay? So for that would require some communication before the game starts. We don't allow for, well, they can make binding agreements, but then the game will change. So we will assume that they will not be able to make binding, they will not be able to sign binding contracts. So by choosing a common random device, can they do any better? Okay. So first of all, what do we mean by a common random device? So we do have to go a little bit into probability theory. So we have a random experiment. Random experiments is denoted with a set of outcomes. So let me denote that with capital omega. Of some random experiment. Actually, let's start with on one side, I'll give the mathematical definition. On the other side, we'll construct an example. So the example that we were considering last lecture, the random experiment we were considering last lecture was the weather condition that evening. Okay? So in that case, omega would be rain, which I'll denote with R. So it will be a rainy evening, or a clear sky, which I'll denote with C. Well, they could have used a different random device. For example, they could have asked one of their friends to toss a coin twice. Okay? Toss a fair coin twice. So the set of outcomes in that case would be the first toss results with the head, the second toss results with the head. The first toss results with the head, second tail. first tail, second head, both tail, okay? And then when we talk about random experiments, random devices, we need a probability measure on the set of outcomes. So we'll denote that, I'll denote that with pi. Okay. By the way, again, for now, we're assuming that omega is non-empty. I shouldn't write that, but we're also assuming that it's finite, okay? Because we're going to use, again, the von Neumann-Morgenstern theorem. We're going to use von Neumann-Morgenstern representation of preferences over random, over probability measures, okay? So here, for example, well, it's spring, the probability of rain is equal to the probability of a clear sky. So we can say that, okay. Well, here we said that that's a fair coin. So probability of head is equal to probability of head tail. Well, they're all equal to 1/4. Now, another thing about random experiments, which we usually don't specify in most undergraduate courses, is the information that the observers receive. We don't always see the exact result of the random event. Okay. Well, so that we specify by an information partition. Since we have here two observers, we have capital I, script I sub I. We will call this the information partition for agent I. And what do I mean by that? Again, mathematically, it's a partition of omega. Do you know what a partition is? So a partition is a collection of non-empty subsets of omega, which are that are mutually exclusive, and the union is equal to omega. That's what we mean by a partition. Okay. So what does that partition tell us? It tells us what kind of information agent I receives about the outcome. So we have a partition for each agent. So let's look at this example. Well, player one gets out of, in the evening, looks outside. He exactly observes whether it's raining or whether the skies are clear. So he has perfect information, which we can say that, which we can represent by subsets of omega consisting of single outcomes. So he exactly knows if it's raining, exactly knows if the sky is clear. Okay. Then these are mutually exclusive, that is, their intersection is empty. Okay, and their union gives omega. So that's an information partition for player one. And the same thing for player two. Well, let's change the story here a bit. Okay, so we asked the friend to toss a coin twice. Okay, so this friend reports the result of the first toss to player one and the result of the second toss to player two. Okay, so because of that, player one, for example, when he's reported that the first toss resulted with a head, he knows that the outcome is one of these, but does not know which one it is. Okay? He knows that it's not one of these. He knows that it's one of these, but does not know which one. If the friend who tossed the coin said the first toss resulted with the tail, then player one would know that the outcome is one of these, but would not know which one. Okay? So player one's information partition would be, again, it's a set of subsets. It's a collection, it's a class, it's a set of subsets of omega. So the first one consists of HHHT, which represents the situation that he cannot tell whether the outcome is HH or HT when he's told that the first toss resulted with a head. And the second partition is tail, head, tail, tail. Okay? That's the information partition of player one. So just by looking at this, I can easily tell, so the first player can tell whether the outcome is in this set or is in this set, but he cannot tell which element it is. Okay? So just by looking at this, I can conclude that player one can tell the result of the first toss, has information about the result of the first toss, but does not know the result of the second toss. And the result of the second toss is only reported to player two. So players two information partition consists of what? Again, it's a subset of this, and it should be such that by looking at that structure, I should be able to tell what player two knows about the outcome. Yes, sir. H, H, and TH. That's one set in the partition. And the other one? Okay, does everybody agree? Okay, very simple idea. So we can, the second player is only reported about the result of the second toss. Okay, so if I tell you that the second toss resulted with a head, you would know that an outcome in this set is realized, and you would know that an outcome in this set is not realized. Okay, so you would know that this event in the language of probability has occurred, but you would not know which outcome. You would not know whether it's head-head or tail-head. Okay? If you're player two and I report to you that the second toss resulted with the tail, you would know that the outcome is not in this set. Again, in the language of probability theory, this event did not realize. You would know that the outcome is in this set for sure. So you would know that this outcome, this event has realized, but you would not know whether the first toss was a head or a tail because you're not given that information. Okay? So far, so good? So far, so good? Okay? So, a triple consisting of set of possible outcomes, a probability measure over set of possible outcomes, and an information partition for each player, which tells us what the agents know about the result of the random experiment. Okay? We call a probability space. Now, given this space, while we're doing game theory, so these agents will have to choose an action. Okay? So, in the story that we gave last lecture, we said, well, before they leave home, this couple will agree on the following. Okay? Player one would say, if it's rainy, I'll go to the opera. If it's clear skies, I'll go to the soccer match. Okay? And then the same thing for player two. Okay? So what they did is choose an action based on the result of the random experiment. Okay? So that we will give a special name. Given a probability space, can see the slide, right? A correlated strategy of agent I is a function. So this time let me denote that with sigma I. Okay. From omega to Si, from the set of all possible outcomes to Si. Maybe you should not write at this moment because we might have to do some fixing. Okay? So, I'll keep that in mind. Let me switch boards. So again, we'll do parallel. So, if they're using this random device, this probability space, then what is a correlated strategy for player one? So sigma 1 is a function from omega to S1. So for example, sigma 1 R equal to opera, sigma 1 C equal to S. Okay? So that was the strategy that we just talked about. If it's rainy, I'll go to the opera. If it's clear, if there's no rain, I'll go to the soccer match. That's one correlated strategy of player one. Another one could be sigma 1 prime, sigma 2 prime, sigma 1 prime, R. Oops. So I'll go to the opera no matter what. That's another strategy. Okay? So far, so good? So let's write one for this random experiment. Okay? So again, sigma 1 is a function from omega, the result of the random experiment to S1. So I have to specify sigma 1 HH, sigma 1 HT, sigma 1 TH, sigma 1 TT. Okay? So a correlated strategy is a complete plan of action. It's a plan of action that tells what the player will do based on the result of the outcome. So here we had one complete plan of action. If it rains, what will he do? If it doesn't, what will he do? So give me a complete plan of action if they decided to use this random experiment. So they agreed that at 5:30, when they're leaving their office, one of their friends will toss a coin once, give a call to player one and say the result is a head, and then toss it again and give a call to player two and say it's a tail. And based on that information, we should write what actions they would take. Yep?
It could be opera,
Opera, sucker, sucker. Right? That's one plan of action. Okay? Okay? That's one correlated strategy, one plan of action. Any other plans of action? For example, opera, sucker, sucker, opera. No? Why not? Exactly, right? So the problem, as your friend said, and probably our other friends noticed, he doesn't know whether the outcome is head, head, or head, tail. If he doesn't know whether the outcome is head or head, tail, how can he choose different actions? Okay? Their friend will just say the first toss resulted with a head. So he will think that either this or this realized. But we cannot tell anything more than that. Okay? So whatever he chooses for this outcome, he should choose for this outcome. Okay? So far, so good? So this cannot be a correlated strategy of player one. It cannot be a complete plan of action because he cannot base his actions on things that he cannot know. He cannot observe. He cannot deduce. Okay? So far, so good? So, which means that I need a condition here. Well, I can change this. I could say that sigma I is a function from the class of information partitions to SI, okay, which is actually more reasonable. But then it will cause some technical problems. You know, you clear this part, you get mess at some other place. For that reason, what we're going to do is we're going to keep this definition from outcomes to strategies, actions, but we will require that this property hold, that is a function such that take any outcomes, omega, omega prime, in capital omega. If there exists a capital, well, I shouldn't use that. If there exists, don't confuse this with indifference, okay? That's a information set in the information partition for which both omega and omega prime are in, okay? If there exists an information set in the information partition of player I, such that both omega and omega prime are in the same information set, then sigma I of omega should be equal to sigma I of omega prime. Okay? So we should not have anything like that. So because HH and HT are in the same information set, the actions taken for those two outcomes should be the same. That's what it says. Okay? So far, so good? Yes? Yes, sir.
All elements of information partition.
Sorry?
I'm not that existent elements of a script
For all? No, but you see, I might, for example, if I take, so it says take any two outcomes, omega, omega prime. So let's say that this is omega and this is omega prime. Is there any information partition which includes both of them? No. That's why we have that condition. Okay? And if I take HH and HT, the first information set, that is, this information set contains both of them, but this one contains neither. Okay? Okay? But thank you for bringing that up. Okay? So intuitively, it just says that if the player cannot tell which one of those outcomes is realized, then the plan should be such that he takes the same action in both of those. Okay? Roughly what this says is that correlated strategies, plans of actions, are actually functions from information partitions to outcomes. Okay? So he tells what he would do if he thinks that this event is realized, and what he would do if he thinks that, well, not think, if he knows that this event has realized. Okay? Okay? This is a little awkward way of saying that, but if we say it like that, when we're writing expected payoffs, it will become easier. Okay? So far, so good? So far, so good? Okay. So now, the game Well, initially, I erased the game. We had the original game where the players were to choose between going to the soccer match or an opera show. Then we looked at the mixed extension in which players were deciding on which independent random device they would use to choose their action. Okay. Now, what we have is they decide on a common random device. Okay. They decide on a common random device. This device, or many other possibilities. Okay. Or many other possibilities. And then once they agree on a random device, what do? They choose a plan of action. They choose a correlated strategy. Okay? So what we require is that correlated strategy profile is actually a Nash equilibrium, a Nash solution of the game of choosing correlated strategies. Okay? Or in another way, I have to erase, so let's erase this part. We don't need this anymore. Again, we assume that these UIs are Bernoulli payoff functions, okay? Because we're going to use expected values. We're going to use the von Neumann-Morgenstern expected payoff representations. Okay. A four-tuple. So first, we need a random device. We need a probability space. Oops. Okay. And then given the random device, we need a strategy profile. Well, that's given the preferences are here. We need a strategy profile. Okay. Here, where this triple is a probability space. And for each I in N, sigma I is a correlated G. Okay. So that's a side mark. So a four-tuple is a correlated equilibrium or solution concept, was a correlated solution of gamma if and only if well, we do the usual game. We take a player, okay, we look at his expected payoff that he would get by using the correlated strategy sigma I. Okay, so we look at the expected payoff he's going to get. So we're going to look at the expected payoff that he's going to get when he uses the correlated strategy sigma I, and his opponent uses or plays according to the correlated strategies given in this profile, okay, which I'll denote as usual with sigma minus I. So this is a list of correlated strategies of all the agents except agent I. Okay. So Well, let's first calculate that expected payoff before writing the rest. What is his expected payoff if all the players play according to this correlated strategy profile? What is the expected payoff of player I if they play according to this correlated strategy profile? Come on, find it. Should not be that tough. Come on, get your pens, your head and your brain and pen working. Don't just stare at the whiteboard. It's not there. What would the expected payoff of player I be if they all played according to the correlated strategy profile, sigma? Okay, let me call this whole thing the profile sigma. And if anybody wants to share their finding with me, I'd be happy to take a look. Scrap paper. Oh, you have a... Okay, well, several of you got the right answer, which makes me happy. So what happens? Well, first of all, the Bernoulli utility functions are defined over strategy profiles, right? They're defined over strategy profiles in the original game. Pure strategy is defined over pure strategy. So when we say UI, and we take the average, weighted average, when we say expected payoff, we're taking the weighted average of the Bernoulli payoffs. But the Bernoulli payoffs are functions of strategy, pure strategy profiles. So what we have to ask is, which strategies will they use? Well, it depends on the outcome. So if the realized outcome is omega, what is the action, the strategy that player I will play? He will play sigma I omega, right? That's the action that player I will take because they're behaving according to this plan of action, this correlated strategy. What would the opponents do? Well, again, they will behave the similar way. So for short, we will write sigma minus I omega. Okay. Given their observation about the outcome, they will choose an action, a strategy, a pure strategy. Well, for any player, it would be sigma j omega, where j is any element in n. So j equals to I here, the other agents here. That will give us a strategy profile. And this is the Bernoulli payoff of agent I as a result of this action. Okay? But then maybe omega did not realize. Okay? Maybe some other outcome realized. Okay? So what do? We take the weighted average of the Bernoulli payoffs, and the weights are the probabilities of these, the outcome omega being realized, which is given as pi of omega, right? So what do? We sum this over the set of all outcomes. Okay? So far, so good? So far, so good? Any questions? Okay. Sure. So, okay. So, what we do is, once the outcome omega is realized, do you agree that the players will play this strategy profile? And as a result, his Bernoulli payoff is going to be this. So the next question we ask is, with what probability will the outcome omega be realized? Well, that's governed by the probability measure, cap pi, right? So pi times omega is the probability that the outcome omega would be realized. As a result, again, you have to be careful. I'm going to say something which is not exactly formally correct. As a result, player I would get this Bernoulli payoff. Okay? Actually, he might be getting this Bernoulli payoff at other outcomes too, but they will be counted separately here again. Okay? So you might get the same payoff at different omegas. Or they might play the same strategy profile at different omegas, but that will be accounted for when we sum up overall omega. Okay? Yes, sir.
We are finding expected result of using correlated.
Exactly. So if this is the random device that the players agree on, and if this profile is the correlated strategies that they use, this is the expected payoff, okay, of player I. Okay, so far so good? That's simple. Now, player I could think, well, the other guys are playing according to sigma I. Well, I can play something else. Okay, so if he plays something else, what would his expected payoff be? Well, he's going to use a different plan of action, different correlated strategy. Let's call that sigma I prime. In that case, when the outcome, let me write it here. When the outcome is omega, he's going to take the action sigma I prime omega. But the other agents are sticking to their correlated strategies at sigma. So we do the same exercise. Find the expected payoff of player I when he switches to another correlated strategy, but the other players stick to the same correlated strategy. Okay? So sigma would be a Nash equilibrium of the game of choosing correlated strategies if and only if this number is at least as big as this number. Or this animal, this four tuple, we will call it a correlated equilibrium or a correlated solution of the game gamma if and only if his expected payoff from sticking to sigma is no less than his expected payoff by switching to some other correlated strategy, given that the other players stick to their strategies, correlated strategies in this profile, and given this probability space. That's it. Okay, so far so good? So far so good? Any questions? Yes, sir. So, yes, we wrote them. Now we have to, let's put the quantifiers. Of course, you see, once you write these things, you have to make sure, always check. There's an I. Where did the I come? It's not a parameter, so it should be quantified for every I in N. There's an omega. Where did it come from? Well, we're summing over it, so omega comes from here. There's a sigma I. Where did it come from? Well, it's given here. Sigma minus I, it's given here. And then there's sigma I prime. It's not given here. It's not a parameter, so it should be quantified. So for any, I'll just write it shortly, correlated strategy. Sigma I prime of agent I. Okay? So far, so good? Any questions? Any questions? Any questions? Well, let's finish our example then. Let's start with this. Random divide. So, by the way, look, unlike a pure strategy, unlike a mixed strategy profile or a Nash equilibrium of a mixed extension, a correlated solution is a complicated animal. Okay? There's a common part, and there's a part which belongs to each other. So it's not just sigma I. It's the whole thing. Okay? So when you're specifying, well, with this definition, we're going to change this. Okay? That's why I said, a mathematically more sophisticated method, but it's intuitively more appealing. Rain, what would you do? Clear skies, what will you do? Okay? We'll simplify this definition. We'll find a simpler mathematical object which will be equivalent to this. Okay? But for now, let's keep working on that. So for now, whenever we see a correlated strategy, a correlated solution of the game gamma, we mean a 4-tuple, an object consisting of 4 elements. Okay? So let's take this group. Okay? And then the strategy, the correlated strategy, sigma 1 R equal to sigma 2 R. That's equal to, when it rains, they go to the opera. Sigma 1 C equal to sigma 2 C. That's equal to soccer. By the way, again, I'm abusing language. When this is player 1 going to opera. This is player 2 going to opera. Actually, they're not equal, but we're abusing language. We're writing them as equal. Okay? Okay, so is this 4-tuple a correlated solution of the battle of sexes game? Okay. Is this 4-tuple a correlated solution for the battle of sexes game? Well, what we have to do is check this. Okay? We have 2 minutes. At least let me start writing it. So let me try to use that table. Maybe it will make things easier. Outcome. Well, with this random experiment, there are 2 outcomes. Rain, no rain, clear skies. Okay. And then the actions. So let me write sigma 1 omega, sigma 2 omega. Well, if this is the outcome, their action is going to be player 1 is going to go to the opera, player 2 is going to the opera, so the outcome is going to be, the actions would be, let me write it like this to note that it's different than 0. And then if it's clear skies, they'll both go to the soccer match. So here, let me write expected payoff. Okay. So let's concentrate on player 1 of agent 1. Okay. So what is his expected payoff? Well, it will be rainy with probability 1/2. It will be clear with probability 1/2. So his expected payoff is 1/2 times U1 of 00, which is, well, I erased it. Player 1 was the one who preferred soccer, so 00. That's 1/2 times 1 plus, with probability 1/2, the sky will be clear, no rain. So they go to the soccer match. And the Bernoulli payoff of player 1 from both going to the soccer match is 2. So his expected payoff is 3/2. Okay. So now I'm going to write sigma 1 prime omega, sigma 2 omega. Okay. But let's take a break. After the break, we'll finish the table. Okay.